So today we're going to start talking about our unit on bonding, and we're going to talk about different types of chemical bonds, a little bit about electronegativity and dipoles. So let's talk about bonds first of all. So bond energy is the energy that's required to break a bond, and there are several ways to form these aggregates. And we usually want to pick the way with the lowest amount of energy, so it's kind of like the path of least resistance. So let's talk about some different types of bonds. So an ionic bond, is a formation of any ionic substance when an atom that loses electrons relatively easily reacts with an atom that has a high affinity for electrons. So they make a good pair. One wants to lose electrons, the other one wants to gain electrons. This usually means that an ionic compound is going to be a metal and a nonmetal. Metals want to give up their electrons. Nonmetals have a very high affinity for electrons. So, for example, sodium and chlorine are an ionic bond. Sodium's our metal, chlorine is our nonmetal. Okay, when we talk about ionic bonds, we also have to talk about what's called Coulombs Law. It is used to calculate the energy of interaction between a pair of ions. And so here's our equation. And so E represents our units of joules, or energy. R is the distance between ion centers. So if we have our sodium and our chlorine ion, we're looking from the center of one to the center of another, and we're measuring that distance. And so that's our R, it's in nanometers. And then Q1 and Q2 are the numerical ion charges. So for sodium and chlorine, we're talking about +1 and -1. And so let's take a look at, for those ions, what we would have. So here's our constant, our 2.31 times 10 to the -19 joule times nanometers. Here's our Q1 and our Q2, so we have our +1, -1. This is the distance between the centers. This would be something that would have to be given. And we get -8.37 times 10 to the -19 joules. If it's negative, that means there's an attractive force, it's lower in energy, and positive means there's a repulsive force, which is higher in energy. So our ionic bond, we're going for the lowest energy and that attractive force between the positive and the negative. Okay, so let's talk a little bit more about bond force. This develops when two different atoms react to form oppositely charged ions. And so if we have the same type, so you would say, okay, well, we're forming oppositely charged ions. What happens if we put two of the same type of atom together? And we have three energy terms. One is electron repulsion. Okay, so that's going to provide some repulsive energy. The second one is proton repulsion. So again, repulsive energy. And the third one is proton-electron attraction. And so that's our third type of energy, or our third energy term. So we want a system that will achieve the lowest energy. We talked about that kind of path of least resistance. And so we can also look at bond length, which is the distance where the energy is minimal. So all these things are relating to having the lowest energy. So if we look at, we're talking about what happens when we put two of the same type of atoms together. An H2 molecule is more stable than two separated H atoms by a certain quantity of energy. It's more stable by this amount, and we call that amount the bond energy. Okay, so let's talk about the other main type of bonding, which is covalent bonding. This is where electrons are shared by the nuclei of the atoms. And if we have two identical atoms, they are sharing the electrons completely equally. So any of our diatomics or things like that, where we have two of the same atom put together. Okay, then we can have a polar covalent bond. These are more common. This is an intermediate type of bond. They are shared, but not equally. And so the electrons aren't completely transferred. They spend more time next to one atom than the other, but we still say they're kind of shared. And so, for example, hydrogen and fluorine are a good example of this, because they're going to form a polar covalent bond. When we form polar covalent bonds, we also have what are called fractional charges or partial charges, and it's this weird symbol, and it can be positive or negative depending on electronegativity and where those electrons are going to be located. Fluorine has a stronger attraction for electrons than hydrogen, and so we will get to this in a second, but if we wrote out the bond, Because fluorine is a stronger attraction for electrons and electrons are negative, it gets the partial negative, and hydrogen then gets the partial positive. Electrons are going to spend more time with fluorine than they are with hydrogen, so this is like our cloud of electrons. And so because there are less hydrogens or less electrons with hydrogen, it's partially positive. Okay, so we talked a little about that electronegativity. Let's go into that in more detail. So electronegativity is the ability of an atom in a molecule to attract shared electrons to itself. So it's attracting electrons that are shared within a bond. And this was discovered by Linus Pauling, so he had a lot to do with electronegativity. And so basically what we do is compare an H to X representing an element, bond energy, with the expected H to X bond energy. And how we get the expected is by taking the average of an H to H and an X to X bond energy. And then that becomes our expected. Okay, and we compare that to the actual. If there is a difference, we say that the bond is polar. So if X has a larger electronegativity than hydrogen, the electron is going to be closer to that X atom, giving it the partial negative charge, like we talked about with the fluorine in the previous example. This trend of electronegativity, if you take a look at a periodic table, increases as you go from, I don't think that should be right to left because these are the highest in electronegativity. So this should be left to right. So we have the biggest electronegativity this way and this way. So the largest electronegativity values are those nonmetals in the upper right-hand corner, and our smallest electronegativity values are those metals in the lower left-hand corner, because they want to give up their electrons anyway. Okay, but if we're talking about nonmetals, these have the highest electronegativity. Okay, so let's relate electronegativity to bond type. If the electronegativity difference, so each atom has its own electronegativity, if you subtract between the two in a bond and you get 0, then that bond type is covalent, and we would say that it is very covalent because those electrons are shared completely equally. This would be any sort of diatomic or anything where the atoms were identical. If your electronegativity difference is intermediate, we usually say that it is less than 2, then you have what's called a polar covalent bond, where they're shared but not equally, and so we would say that our covalent to ionic character is somewhere in between those two. If your electronegativity difference is large, so we would say greater than 2, then you have an ionic bond, and we would say that the character is very ionic. So we kind of have the spectrum from covalent to ionic. So let's take a look at an example. So I'm going to order the following bonds according to polarity. So I've got an electronegativity chart over here. So H to H, we know that if they are identical, that difference is going to be 0. So now if we look at the O to H bond, if we take a look at our electronegativity, here's oxygen, here's hydrogen, okay, and so that difference, we have 3.5 minus 2.1. If we look at the chlorine to hydrogen, chlorine, where are you? Okay, so we've got chlorine in the halogens, so our difference with chlorine to hydrogen is 3.0 minus 2.1. If we look at sulfur to hydrogen, we've got 2.5 to 2.1, and then fluorine to hydrogen is 4.0 to 2.1. So noticing that that fluorine atom has that largest electronegativity, and it's also in the upper right-hand corner. So now if we were to rank these according to polarity, well, the hydrogen to hydrogen has no polarity, and then we're looking for the smallest difference to the largest difference. So it looks like sulfur to hydrogen would be next, and then chlorine to hydrogen, and then oxygen bonded to hydrogen, and then our fluorine bonded to hydrogen. So if we take a look, the electronegativity values are going to increase as we go towards that upper right-hand corner. Okay, so let's relate this to some dipole moments. Okay, so molecules that have this center of positive charge and a center of negative charge are said to have dipole moments. And we indicate this by using an arrow pointing toward the negative center and a tail at the positive center. And so we draw an arrow like this being our electron or our heavy or our negative area, and this being our partial positive area. So we can also use what's called an electrostatic potential diagram to indicate these areas of positive and negative charge. Red means that it's electron rich, and blue means it's electron poor. And so we can also have polyatomic molecules. Remember, polyatomic, poly means more than one, that also exhibit dipole behavior. And so we can have oxygen, hydrogen, hydrogen. Oxygen has a larger electronegativity, so it's partially negative. Each hydrogen is partially positive. And because these won't cancel, we have what's called a dipole in the direction towards the oxygen because of that pull of the electrons. Okay, some molecules will have polar bonds but won't have a dipole moment because they cancel out. So if we look at CO2, CO2 looks like this, and we will talk about Lewis structures again. But carbon is partially positive. It's got a smaller electronegativity value than the oxygens, and so we do have these dipole moments, but they're canceling. Or we would say that these are polar bonds, excuse me. These are polar bonds, but they cancel, and so we have no dipole moment because they cancel out. Okay, so here's those electrostatic potential diagrams. Remember, red represented electron-rich or our negative areas, and then blue, or purple in this case, looks kind of purple, is our partial positive. So again, here's our definitely partial positive, here's our partial negative, and then this doesn't really have a polarity, it's kind of in the middle. So let's look at an example of this. So for each of the following, show the direction of the bond polarity and indicate which ones have a dipole moment. Okay, so we have HCl. Hydrogen has a smaller electronegativity than chlorine. And so because there's only two of them, it is going to have a dipole, and it's going to be towards the chlorine. Okay, if we look at Cl2, we know that because they are the same, there's no partial charge and there is no dipole moment because there's no polarity. Okay, SO3. So we have sulfur, and then an oxygen, an oxygen, and an oxygen. And oxygen has a larger electronegativity value, so it gets the partial negative. Sulfur is partially positive. Now, each of these is a polar bond, but because of the orientation of the oxygens, they're all going to cancel out. This is what we would call trigonal planar geometry, and we'll talk about that later in the chapter. So this would be polar bonds, but no dipole moment. Let's look at CH4. So we have our carbon, we have a hydrogen, a hydrogen, a hydrogen, and a hydrogen. And remember, we draw these squiggly triangles and the solid triangles indicating that it's pointing into and out of the plane, and the lines indicate it's in the plane. Well, in this case, let's see, carbon is more electronegative, and we could write our partial charges for each hydrogen because the bond is the same. Now again, we have polar bonds here, but because of the orientation of the structure, they're all going to pull evenly and cancel out, and so we have no dipole moment here, even though we have polar bonds. Alright, let's look at our last one, which is H2S. So we have sulfur, hydrogen, hydrogen, lone pair. Sulfur is more electronegative, and so we have a pull. Now here is where we have some polar bonds, but they aren't going to cancel because of the orientation, and so we do have a dipole moment in this case. Okay, so here are the checks for understanding for Section 1 Bonding Intro. So number 1, compare and contrast ionic, covalent, and polar covalent bonds. Number 2, explain Coulombs Law and significance. Number 3, how does electronegativity contribute to bond type, and what is the trend for electronegativity? And number 4, what is a dipole moment and how is it indicated? Can you have a molecule with polar bonds but no dipole, and can the reverse occur? And explain this. Alright, we'll discuss this in class. Have a good day.